Now let's talk about how we can calculate work and also introduce the concept of path-dependent and independent variables. If we wanted to calculate work for a process where you have the expansion or a compression of a gas against some external pressure, we would use the following equation. Work is equal to negative P external, right, that's our external pressure, times the change in volume. It's beneficial for us to think about why there's a minus sign in this equation. And so to see why we need the negative sign in the equation, we're going to consider two situations. We're going to consider the expansion case and we're going to consider the compression case. So starting with our equation, work equals negative P external times delta V, we can consider what would happen if an expansion occurs. Let's think about what the sign of delta V is for an expansion. For an expansion, the sign of delta V should be positive, and the external pressure is going to carry a positive value. There's no such thing as a negative pressure, and so P external has to be a positive number. The negative sign out in front of the equation makes it so that you're multiplying a negative by two positives. When you multiply a negative by two positives, you should get a negative sign for work. And that is exactly what the sign convention is that was defined a few videos ago. So that negative sign is necessary in order to ensure that you attain the correct sign convention. Now, we could also consider the case of a compression. And in the case of a compression, we have that the change in volume is negative, right? Volume decreases when something is compressed. The external pressure is still positive, right? Because there's no such thing as a negative pressure, so P external has to be a positive number. And the negative sign that you have out in front of the equation makes it so that you're multiplying two negatives by one another. When you multiply two negatives, they wipe one another out, and you're left with a positive value. And so you get that work is positive in a compression. And that is totally consistent with the sign convention that was previously defined. So this is why the equation W equals negative P external times delta V has a negative sign out in front of it. It is to help keep you totally consistent with the sign conventions that we've defined for work. Let's now use the equation to do a calculation of work. We're told in this example that a gas is expanding from 10 liters to 30 liters against a constant external pressure of 2 atmospheres. We need to calculate the work for this process, and we're told to do it in units of joules, which is a unit of energy. It's so important that you always write out the units. And you will see as we go through this practice calculation that the units that we initially will get will not be what the question is asking for. There's going to be a conversion factor that's going to have to come into play to get us to the units that we're looking for in the problem. We have work equals negative P external times delta V. And I'll tell you that anytime you see a delta, that always means final minus initial. So delta V means V final minus V initial. Now we can plug in the numbers. So we're told P external is 2 atm and V final is 30 liters minus V initial, which is 10 liters. And when you multiply that out, the units that you're going to have are liters times atmospheres, and the numerical value that you're going to have is, we got negative 2 times 30 minus 10 is 20, so negative 2 times 20 is negative 40 liters atmospheres. You might be tempted to stop at this point and put that in as your answer, but the problem specifies that you must report the answer in units of joules. So liters times atmospheres is a unit of energy, but it's kind of an awkward unit of energy that's not commonly used. It is much more common for us to use units of joules. And now we will need to use this conversion factor that you don't have to memorize. It's given to you, but you have to use this conversion factor in order to make the units what you want them to be. So we'll add that step here, negative 40 liters atmospheres. And to make the units what we want them to be, we're going to use the conversion factor in a way such that we put 1 liter atmosphere on the bottom. That will allow liters atmospheres to cancel out. And then we'll put the 101.3 joules on the top because that is what we are going towards. In terms of the units, right, the liters atmospheres cancel. Negative 40 times 101.3 comes out to negative 4,052 joules. And there's our answer. It's also helpful to consider whether or not your answer is reasonable. And to do that, you can recognize that in this problem, we're told that an expansion is occurring. And so that means that work has to be negative. The system is doing work on the surroundings. We get a negative answer, and so we know that our answer is at least reasonable here. Now let's talk about path independence and dependence. Delta E is an example of what's called a path independent variable, or another way of saying that is E is a state function. And what that means is that regardless of how you get from your initial state to your final state, the value of delta E will always be the same, no matter what your pathway is. Now, what do I mean when I talk about a path? So when we do thermodynamic transformations, we could consider maybe heating a gas. And there are multiple different ways that you could heat a gas. One way that you can heat a gas is to heat it at a constant pressure. That's one example of a pathway. Another way that you could heat a gas is to heat it at a constant volume. That would be an example of a different type of a pathway. Because delta E is path independent, it doesn't matter if you heat the gas along the constant pressure pathway or if you heat it along the constant volume pathway, you will get the same value of delta E either way. And we're going to do some calculations and see some equations that end up showing this a little bit later. Q and W, heat and work, on the other hand, are path-dependent variables, and the values that you get for Q and W will change depending on whether you do a process along a constant volume pathway or if you do it along a constant pressure pathway. Now, just to get a little bit of a visualization for this, we could consider a transformation that's shown with this energy diagram where we plot energy versus the progress of transformation. We have some initial energy for our system and some final energy for our system. And the value of delta E will be equal to the final energy minus the initial energy. It doesn't matter how you get from the initial state to the final state. You can go along this crazy path up here, or you can go along this crazy path down here. And no matter what, you're going to still have the same value of delta E no matter what. You can think of these different paths as being maybe a constant volume method or a constant pressure method, or maybe a method where neither pressure nor volume is constant, right? Those are different pathways, different ways that you can transform a system. The values of Q and W will be different as you move along these paths. Now, I recognize that this can be a somewhat abstract concept, thinking about thermodynamic variables, thinking about path dependence and independence like this. And so we could think about a different type of example. Think about an example that we can relate to. So let's say that I wanted to go from my office, which is on the first floor of the chemistry building, all the way up to where my old lab was, up on the fourth floor of the chem building. There are a couple of different options on how I can get from the first floor to the fourth floor. I could take the stairs. I could take the elevator. If I was really feeling dangerous, I could, I guess, climb up the side of the building if I wanted to. And there are going to be some parameters that will depend on which pathway I take, and there will be some parameters that don't depend on the pathway that I take. One thing that doesn't depend on the pathway that I take would be the elevation gain, right? The change in altitude from the ground, right? No matter what, whether I take the elevator or if I take the stairs or if I climb up the side of the building, I'm going to gain about maybe 50 or 60 feet in elevation as I go from the first floor to the fourth floor. That is path independent, no matter how I get there. Some path dependent quantities might be things like the amount of time that it takes for me to get from the first floor to the fourth floor. If I take the elevator, it will be very short. If I climb up the side of the building, it would take me much longer. Maybe the amount of risk would be a path-dependent variable. There's probably not much risk associated with taking the elevator, assuming that the elevator has been well maintained, and you never really know, I guess, with our elevators in the chem building. But it's certainly less risky than climbing up the side of the building. That kind of gives you some, another example, maybe something that's a little bit more relatable, where you can consider a transformation that can occur along different pathways and how there can be some quantities that will be path dependent, and there will be some quantities that will not change regardless of which pathway you go along. That brings us to the end of this section. Next up, we're going to talk about heat capacity and how you calculate heat.